Welcome to AP Chemistry Summer Review Session number 4. We are talking today about the periodic table and some basics of how it's organized, where to find things on it, what it's telling you, and what all of those numbers mean. So again, more basic review for you. Hopefully jogs your memory so that you are ready to go on your test. Okay, how is the table organized? So if you have been in chemistry class before this, if you were to sit down and just think for me right now, here's a periodic table right here, okay? What could you tell me about this periodic table? So, rows, columns, colors, location of different elements, the numbers that are on there. You should know quite a bit of information about that table. And the longer you go in chemistry, really the more information you learn about how that table's organized and how it works together, okay? It's pretty cool how much information you can tell from it. So what could you tell me right now? Hopefully a good bit. If you can't, then keep watching, okay? We'll go over this. All right. So first off, know the parts of the different chemical blocks. So every element has its own block on the periodic table, and we like to learn quite a bit of information from those, okay? So this might be typically, every periodic table is a little bit different, just be aware of that. When you come into class, I will give you your own periodic table that is laminated, and it will hopefully hold up for the whole year for you. And every table is a little bit different. This one puts the number off in the corner. Some of them put the number, I think this one here would put the number directly up and in the middle. So there can be slight differences in how that individual block is set up, but they are basically the same, okay? So your big number is going to be up top in the corner, in the middle, somewhere on this top part like this. And this number is called the atomic number. What does the atomic number tell you? What information can you learn from that number? Good, okay, it tells you the number of protons. So this is telling me that in the silver atom, in one atom of silver, there are 47 protons in the nucleus. It's a fairly large element. Okay, and then Ag is the chemical symbol right here. Sometimes it'll give you the name below it, sometimes it does not. So sorry, in AP Chem you do not get the name. It's one of the things you actually need to know. Is when you come into class, you should know, if I say Ag, you should know that that's silver. If I say K, you should know that's potassium. Al is aluminum. So there's definitely some of these, especially these like bottom two lines here. There's not very many in those bottom two lines that we routinely use. Cesium, francium, some of these, like platinum is right here, gold, lead, polonium maybe, radon. That might be about it. And honestly, the same here. There aren't too many of those that we use. So I wouldn't necessarily expect you to tell me that EU is europium right off the top of your head. But definitely these ones up top, especially the main group elements. So this in the red, orange, top line of 2 lines of blue, a little bit of purple here. Definitely in the green section and pink. You should be able to tell me what those are, okay? So you will have your symbol there for you on the periodic table, but you will not be given the name of the element. So if I ask you where cobalt is, you should be able to say it's CO, it's right here. Okay? And then number on the bottom, this is sometimes what I call the big number or the decimal number. This looks like it's maybe European here. It has a comma instead of a period, but 107.8682. And different tables are also going to vary depending on who the table is built for. Is it built for elementary students, high school students, master's level, research, whatever, with how many decimals they're going to give you. So for this class, whenever you're using your mass number from your periodic table, use 2 decimals for me. Okay, so in your calculations, go ahead and use 2 decimals, all right? So for silver, you'd be 107.8, and then go ahead and round up 87. Some tables will give you more numbers than that, some will not. The other reason I like you to round off is just to keep it consistent. So for instance, we might know hydrogen is, 1.0008, so we know that out to like 4 decimals, but we may not know bismuth out to nearly that far, or we may not know radon out to nearly that far. So just keep it 2 decimals for me to keep it consistent. That is your average atomic mass. Okay, and we get into, when we talk about moles, what that number represents. It typically represents the mass of one atom in AMU. Remember that unit, atomic mass unit, which essentially correlates to the number of protons and the number of neutrons put together. Okay, so average atomic mass if you're assuming that a proton is a mass of 1, a neutron is basically a mass of 1, then that would be the mass of those two put together. It is an average. As you get into moles, that's the number of grams in 1 mole. That's the way we're going to most frequently use that number. It can also represent a few other things. So we'll get into that some more as we go. But just know this is your number of protons, your atomic number. This is your number of essentially protons and neutrons, your average atomic mass. Okay, but then the question always comes up, and I struggled with this one for a while before I really understood what it was talking about. Why is that an average? Why is that a decimal? Why is it not a whole round number? If this is the number of protons and neutrons, I mean, we don't have 0.8 of a proton floating around anywhere, at least not normally. So why is that a decimal? Why is that like that? Okay, so why is the mass an average? And the reason for this is something called isotopes. An isotope is naturally occurring, and it will have the same number of protons. Okay, it's the same element. You have gold, okay, same element, but it can have a different number of neutrons. And that will affect the mass. So if you have gold, and gold is element, let me see, 79, okay, so it probably would have about 79 neutrons-ish, but one might have 79 neutrons, one might have 80, one might have 81, one might even have 88, no, not 88, 78 neutrons. Okay, so the protons have to stay the same, but the neutrons can actually change a little bit, and that will affect the mass of that element. And so what we like to do is to get an average. Okay, so this is an element here, and you might see these on the AP exam actually, something like this. And this is fractional abundance. Basically, think of that like percent. So this would come from a mass spectrometer data, and you take an element and you put it through that mass spectrometer. A mass spectrometer is going to separate it out based on mass, okay, how much it weighs. And so if you have a single element and you put it through there, you'd think, oh, all be the same mass. Technically, they can be a little bit different, and that's what we're talking about here. So we put this through, and most of it came up with a mass of 20. Okay, so the highest abundance or percentage would be right at 20, just a little tiny bit at 21, and a little bit at 22. Well, why? That's what we're talking about. It's because of isotopes. It's because in real life, it's possible to form more than one different isotope. And that actually, like, where do the isotopes come from? When that atom formed, all right, you can have a stable atom with slightly different numbers of neutrons because they're not as important as protons. And so the 20 would be by far the most stable, typically, the one that holds together the best or is the most likely to form, but it is possible to form other ones. And naturally, if you were just to go, say, mine this element, you know, scoop it out of the earth and purify it, and here's just this element, naturally occurring, it could be any of those isotopes, but it does tend to be in a very recognizable pattern. And so to represent that, because we're almost never dealing with just one atom, okay, if you're just dealing with one atom, it's going to have a precise number, weight of 20, 21, or 22, no decimals. But if you have a bunch of atoms and you want the average, then you get a decimal. So you understand how averages work. And that's what's going on here. Okay, so most elements occur naturally as a mixture of isotopes. So to reflect that, we use an average instead of a whole number. And so I'm going to ask you the question, which element is this? So it's mostly 20s, a little bit of 21, a little bit of 22. Where do you think the average would fall? You can do it mathematically if they give you numbers here. So if this was like, say, 80%, you'd take 0.8 times 20 plus, 0.01, whatever percentage they are, and you can calculate it. Here, an eyeball is probably good enough. It's definitely going to be 20 at least, maybe just a little bit more than 20, so maybe 20.1, 20.2, and then go look at your periodic table and find that element, okay, with a mass of about 20.1, 20.2, 20.3, somewhere in there. And if you look through your table, that might be a little bit small, but you should come up with neon. Okay, neon has an average atomic mass of 20.18, and that fits in nicely with what you see here. Okay, so that's how you find isotopes. So we can also write that like this. It's called isotopic notation. So I just told you this, isotope, same number of protons, different number of neutrons, And what is that going to do? It's going to change the mass. It doesn't change the element. It doesn't even change how the element behaves, typically, but it can change the mass of that element. So two things. We write them with your element written in the middle here. Okay, so for like neon that we were just looking at, you'd put neon, the symbol, there. And then if we had the one that was 20, that 20 would go up here. And then the bottom number, the smaller number, and it should make sense, okay? The bigger number is the mass number, the smaller number is the atomic number. So neon is atomic number. Ooh, try to write here. Writing with a mouse is just never easy. We get 20 over 10 neon. Okay, so that tells me that it has 10 protons, atomic number, but up top, it looks like it'd have 10 protons plus another 10, so total of 20 for the mass number. All right, so you can see that here. So atomic number, Z, so you'll sometimes see it as X, which just means whatever chemical symbol you're gonna have it, and then you have A over Z. And don't get those confused. A, I know it should stand, A should stand for atomic number. It doesn't. I'm very sorry. I don't know why it doesn't. A stands for mass number, Z stands for atomic number. I don't know. Just remember that it's flipped from what you think it would be. So basically big number on top, little number on the bottom, protons and neutrons, just protons. And then they can throw things at you like this. 2 plus, right? 2 plus, did it gain or did it lose? It lost because it's a metal, and metals lose electrons, right? Please, gotta remember that one still. Okay, so it lost, but a lot of times they don't. So with that neon that I had earlier, it was 20 over 10. This one did not have any charge on it, right? How do I know how many electrons it has? If they ask you that question, because I know the number of protons, I know the mass number, so if I want neutrons I can subtract. How do you get electrons? Well, to get electrons, you need to remember that elements are typically neutral. So they typically do not have a charge. And unless you are told otherwise, you assume it is neutral. If it's neutral, then it has the same number of protons as electrons. So for this magnesium example, we have protons would be 12, and neutrons, 22 minus 12, would be 10, and then electrons, okay, typically would be 12, but in this case we lost 2, plus 2. So 12 minus 2 is also 10, okay? If this did not have the plus 2, then it'd be 12 protons, 10 neutrons. That does not look like a 10. And, wow. And 12 electrons. Okay, so don't forget how to do isotopic notation if they ask you questions about it like that. All right, repeats in the table. I wear this shirt periodically. So just terms here. Family group is going to be vertical like this across your table, and period or row, that's going to be horizontal. So going like this way, I just think like periods, dot, 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 they go across the page. And so periods go this way, horizontal, row or family goes this way, all right? And we have different names for different ones. So general characteristics on your table, you're gonna have metals and you're gonna have non-metals, right? And so if we look here, you have your staircase, which I can't draw very well at the moment, but it goes right like that. Only a little bit neater than the way that I drew it. So you have your staircase there, and this side, what's on this side? Those are your metals. Upper right-hand corner is going to be your non-metals. Right around that staircase are generally what we call the metalloids. Technically, the staircase is the line, okay? I guess for you that line goes this way. So if you are over here on the staircase, then you are going to be a non-metal, and if you're over here, you are going to be a metal, okay? But around it, we generally call metalloids. There is some debate on this, I suppose, because different tables might have different ones colored differently to show that they're metalloids. Some of them might like include aluminum, not include aluminum. whatever. I've seen different ones, but generally. Okay. Okay, I did want to show you this. This is what happens if you actually put the table completely in one line. Most of the time, these elements right here in this range are shown down here. Okay, and then this is like squished over here, and you have a smaller, like this one. All right, so this big block is right here, and the table's been squished together. That's how we're used to seeing it. Technically, it is actually really long like this, but we don't draw it that way because it's too long for our pages usually. But it is that way, okay? And so that's how it fits. And we learn later why the table is this shape. Why aren't there elements here? Seems like there should be boxes there. Why aren't there elements there? Well, you might remember from Chem. If you don't, hold on. We'll learn it later this year. All right. Boom, spit, fizzle, boom, dud. Woo. Okay. So this is characterizing the different layers of the table. This, if you haven't had me before, this is just kind of a silly phrase I use to help remember it by. So boom is your first group, okay? So this is boom right here, and then spit. All in here is like fizzle, and then I added that one in. I had a student, and so I added it in for this. She would always call it and so I added the in for her. But that's down here, like a little unsure what they're gonna do. They're kind of iffy. And then we have another boom right here, and then dud is this last row. It's a little bit off the page, okay? And that just helps you to remember the characteristics. So the booms are super reactive, like pretty much gonna react no matter what you put them with. If you want to have these things, you have to keep them out of the contact of air because they'll just react spontaneously with the air. They are super reactive. And then boom, spit, it's pretty reactive, like a llama spitting at you, or like you put like spit in water maybe, but not as bad as the booms. Fizzle is like some of them react, some don't. They react like a little. Okay, so fizzle. And then they're hard to characterize. They're hard to say, like they're not really all the same thing there. And then boom, super reactive again, and dud. Okay, so this chart here is information you should already know. If you're not familiar with it, then just go ahead and remind yourself. Definitely make sure you memorize the known charges. That is important for this class. They really just need to know the ones I have here, plus I think I said aluminum is +3, and then silver is +1. Know those as well. So group 1A, okay, that's going to be this group in red over here. That's group 1A. Those are known as the alkali metals. Their charge is +1. They're a boom. Okay, they're very reactive. Group 2A here in orange. Alkali earth, charge of +2. Fairly reactive. I call them the spits. Okay, so boom, spit. Fizzle is your transition metals. Variable charge, I said often +2. You don't have to memorize these because the charge can change. Sometimes, like, some are +2, some can be +2, +4, some are +3, +1, whatever. They're all plus something. Metals lose electrons, but they can differ. And then we skip all the way to 6A. These are nonmetals. The only thing I want to say about 6A, I put charge of -2, -2. Please do remember, so this is 6A right here. Okay, that negative charge only goes down to the staircase. So if you have your staircase, I can draw it a little better this time. Staircase goes through here. Okay, so like oxygen's -2, sulfur's -2, selenium's -2, tellurium's -2, but polonium, and this is livermorium, they would not be negative because they are nonmetals. Okay, they don't really have charges because they're super reactive anyway, but just so you're aware of that. Okay, so I say 6A is -2, but it only includes down to that staircase. All right, so there you go. Then halogens, -1, super reactive, another boom, and noble gases. I put Na, okay? They're noble gases, they're noble, they stick their nose up in the air, and they do not react. So generally, you can force them to react if you put a lot of energy into it. Generally speaking, they're not going to react, okay? So those are noble gases, don't react, I call them duds. Okay, so boom, spit, fizzle, boom, and dud. They don't react. All right, not that. Last slide for us today is then using that information, using the basic charges on the table, metals, non-metals, to actually form a formula, okay, to how do we write formulas. We're going to look at how to name them in a later video, but for today, how do you make a legitimate compound? Okay, so chemical formula, something like this, Al2O3, formula for caffeine, is going to contain symbols and then subscripts, all right? The symbol obviously tells you which element it is, so Al tells me this is aluminum. The subscript tells me how many of that element. So if I have a subscript of 2, I have 2 aluminums. 3 oxygens. Molecular formula, this would be the molecular formula. It's the one you're used to seeing, pretty condensed, tells you everything. And then formula unit is the molecular formula for ionics. And so it would look the same to you. It's technically called something different. That has to do with the fact that ionic compounds can form like huge crystal structures. So we just want the most basic unit of that crystal. But they really are the same thing. Okay, so something like NaCl, wow. Try that again. NaCl. Okay, that's an ionic compound. And we draw the formula like that because for every one Na, there's one Cl. But in reality, you're not just going to have like 2 together. You're going to have this huge, usually cubic-shaped crystal that's full of Nas and Cls. But the ratio is a 1-to-1 ratio. So we write it that way. As opposed to Al2O3, one molecule is just going to have 2 Als and 3 Os. Okay. All compounds are electrically neutral. Okay, woohoo! Start in your notes. Make sure you remember that. That is the key to writing a formula. If they're neutral, then you're going to put them together to make it neutral. So this allows you to predict ionics. Covalence, a little harder to predict. Just go by the naming system from known charges. Okay, so for aluminum, how I knew and how you can know that the correct compound is Al2O3, not ALO, not ALO2, is because of charges. So aluminum, supposed to know this, has a known charge of +3. Okay, that one wasn't in one of our columns, but you need to know that one. So aluminum is +3. Okay, what is the charge of oxygen? It's up here on your table. Group 6A, charge of -2. Okay, so we have a +3 and a -2. We want to make this equal to 0, if you remember doing this. And so you want to figure out how many aluminums, how many oxygens can I put together in the lowest whole number ratio to get 0. And so I said the rule of 2's and 3's. Remember I said if you have 2's and 3's, just flip them. So if you have +3 minus 2, you get 3 becomes 2, 2 becomes 3. And that will work for you. Why does that work? Because you're trying to get to 6. So 3 times 2, the total charge here is +6. And then 3 times -2, the total charge here is -6. So you can see +6 minus 6 equals 0. Check. Smiley face. And you are good to go. All right. Yeah, so there's lots of examples you can do of that. Just look at the charges and do the math so that they equal 0. The same number of pluses, the same number of minuses. Okay, does not apply to covalence. Okay, that is it for today. Hopefully that was helpful. There is more review on our Google Doc and more review online if you would like it. Definitely ask me if you have any questions. I'll see you next time.